Learning objectives. In this lesson, you would be learning about quality assurance and standards and the following in detail. Electronic packaging. Introduction. Welcome to the session on electronic packaging technologies. Electronic packaging is a multidisciplinary subject. It includes mechanical, electrical, industrial engineering, and chemistry. Electronic packaging. It is housing and interconnection of integrated circuits to form electronic systems. Circuit support and protection, signal distribution, manufacturability and serviceability, power distribution. Issues in electronic packaging. Electronic packaging has issues in electrical analysis and testing, mechanical analysis and testing. The problem lies in manufacturing and industrial engineering. During electronic packaging, the market analysis has issues. The problem is evident in thermal analysis and testing. There are issues in reliability, performance, cost, market need and timing, manufacturability, yield, and etc. Hierarchy of interconnection. First, the gate-to-gate interconnections on the silicon die need to be done. Then the connections from the chip to its package should continue. Next level connection should be between PCB, from component to component or to external connector carried out. Next level of package must be between PCBs, including backplanes or motherboards need to be done. Next level package would be the connections between sub-assemblies, for example, a rack. Then the connections between physically separate systems should be done. For example, an Ethernet LAN. Blue jean, example of connection hierarchy. 3 packaging technologies. Through-hole mounting, surface mount technology, chip scale packages, CSP. Through-hole mounting. The pins of the components go through the previously drilled PCB holes. Benefits. Easy to solder, either automatically or by hand. Easy to desolder and test. Implement interconnections between upper and lower layers via in non-plated hole technologies. Drawbacks. Signals must necessarily go through all PCB layers. Low density due to minimum pin diameter and only one-sided mounting. Surface mount technology, SMD. The pins of the devices are mounted directly onto the surface of the PCB. Benefits. Much higher density. Pins can be thinner. Devices can be mounted on both sides of the PCB. Components do not block signals in inner layers. Higher degree in the automation of mounting process. Less parasitic inductance and capacitance. Reduced cost. 1/2 to 1/4 and size. 1/4 to 1/10. Drawbacks. Poor manual solderability and repairability. Reliability issues due to thermal and mechanical stress during soldering and operation. Different thermal expansion and coefficients. Classic verification procedures no longer valid. Chip scale packages, CSP. Chip scale package or CSP is a single die direct surface mountable package with an area of not more than 1.2 times the original die area. CSP is not a new mounting technology, it is an evolution of SMD. The passive components surrounding the chips must also be miniaturized, resistors, and decoupling capacitors. Benefits. CSP is the only way to achieve pervasive and ubiquitous computing. Further improvement in high-speed performance. Drawbacks. Difficulty in PCB fabrication and mounting due to minute pin pitches, 0.5 mm. Long-term reliability not studied, not serviceable. First step of packaging, the silicon wafer. The problem, how do I know that the chip is going to work before packaging it? Solution, test it, but this is not easy to achieve. Probing pads 150 μm away. Area array pads. Powering the chip. Removing the heat it generates. Testing it in a reasonable time. Only a limited testing, if any, is usually performed. Full testing is done after packaging. A typical low-density SMD process from silicon wafer to package. Wafer preparation, dicing, die attach, wire bonding, molding, solder plating, marking, lead trim and form. Wafer preparation and dicing. Wafer preparation. Wafers are mounted on a laminating tape that adheres to the back of the wafer. It holds the wafer throughout the dicing and the die attaching process. Dicing. The die sawing machine using a diamond saw blade saws the wafer into the individual die or pellet on the adhesive backing tape. Deionized water and carbon dioxide bubbles are dispensed on the wafer to remove silicon dust or debris, besides lubricating and cooling down the blade. Die attach and wire bonding. Die attach. The die attach machine will pick up the die and deposit on the frame. It may utilize the wafer mapping method to pick up only the good dies. For most processes, die attach materials like gold or lead tin based solder wires or silver epoxy paste potting on the frame are required prior to die bonding process. Wire bonding. Either gold or aluminum wires are used depending on application. Bonded one at a time, the wire is fed through a ceramic capillary. With a good combination of temperature and ultrasonic energy, a good metallized wire bond is formed. Molding and solder plating. Molding. The molding process aims to encapsulate the whole wire bonded die against exposure to contamination and other physical damages. The lead frames that hold the dies are placed in individual cavities which are filled with liquid resin. Solder plating. This step provides a layer of tin lead solder on the lead frame for making easier PCB assembly process. Lead-free finishing with tin bismuth plating or tin copper dipping can also be used. Marking and lead trim or form. Marking. Marking is the coding process that writes customers' corporate and product identification code on a packaged device. It commonly uses a laser-based machine. Lead trim or form. The final process is to trim away the leads of the packaged device from the frame trip. The leads are cut and formed mechanically to the specified shape. Chip attachment to the package substrate. The die attachment compound should provide electrical grounding, thermal dissipation. There are three alternatives: soft solder die attach, epoxy die attach, and metal-filled glasses. Soft solder die attach. This process uses a solder material to bond the die to the lead frame. The solder is introduced as a wire per form and melted onto the hot lead frame surface as a liquid solder dot. Epoxy die attach. Epoxy die attach is the most commonly used process. Usually, silver-loaded polymers are used, but the term generally encompasses the use of other adhesives such as polyamide or silicon-based materials. Metal-filled glasses. Less used because of the high temperatures needed. They have been used in ceramic packages. Points to pay attention to: different CTEs, fatigue, and creeps. Chip package connection wire bonding. Connections are made from the chip to the pad frame via thin wires. Typically 100 by 100 μ metal pads on 200 μ pitch. Mechanical bonding of one pin at a time. Sequential. The wires are made of low resistivity alloys or doped metals, gold and aluminium, also copper and silver. Typically 25 μ diameter for logical devices. Drawbacks of Wire bonding. Slow process. 1 pin at a time. Speeds from 4 to 10 wires per second. Pads are limited to the chip periphery. Low pad density and reduced pad pitch. Up to approximately 500 pads. Electrical limitations. High inductance of wires. Crosstalk between adjacent wires. Chip package connection. Tape automated bonding. The interconnections are patterned on a multi-layer polymer tape. The tape is positioned above the bare die so that the metal tracks on the polymer tape correspond to the bonding sites on the die. Advantages: smaller and closer pads, high density up to 850 pins, better electrical characteristics, faster procedure but more expensive machinery. Chip package connection. Flip chip. The chip is soldered to the package substrate using the solder balls, bumps that have been grown over the die pads. Flip chip is currently the preferred process for high-end integrated circuits. High frequency of operation, small size and many input-output pins. Advantages: improved density. Pad pitch and size is not better than in wire bonding, but input-output pads can be distributed all over the die, not just in the borders. Reduced inductance due to the elimination of wires and better power and ground behavior. Faster process. All the pads are soldered at the same time. Drawbacks. Alignment is critical. Although there is some tolerance due to its self-alignment property. Mechanical stress due to different thermal expansion coefficients of the silicon and the package substrate. Flip chip no longer pad limited chips. Core limited, pad limited, area array pads. Flip chip. Growing the solder bumps. There are many techniques. A bump is typically 70 to 100 μm high and 100 to 125 μm in diameter. Current materials for the bumps are SNPB, eutectic, high lead or lead-free compositions. Flip chip concept at the board level. BGA packages. Materials used in electronic packaging. Materials: semiconductors. Applications: CGAS. Material: metals. Application: solders for interconnectors. Gold wire bonds. Copper lead frames. Copper traces in substrates. Tungsten. Molybdenum traces in confired ceramics. Silver, gold for thin and thick films on ceramics and nickel diffusion barrier metallizations. Material: ceramics. Application: aluminum oxide substrates modified with barium oxide, silicon dioxide, copper oxide, etc. Silicon mononitride dielectrics, diamond heat sinks. Material: polymers. Application: epoxies, filled epoxies, silica filled anhydride resin, conductive adhesives, laminated epoxy, glass substrates, polyimide dielectric, benzoclobutene, silicons and photosensitive polymers for photomasks. Material: glasses. Application: silicon dioxide fibers for optoelectronics, silicate glasses for sealing, borosilicate glass substrates, and glass fiber for epoxy or glass substrates. Metals. In a metal, the outer electrons are shared among all the atoms in the solid. Each atom gives up its outer electrons and becomes slightly positively charged. The negatively charged electrons hold the metal atoms together. Since the electrons are free to move, they lead to a good thermal and electrical conductivity. It is impossible to see through metals since these valence electrons absorb any photons of light which reach the metal. No photons pass through. Metal alloys. Alloys are compounds consisting of more than one metal. Adding other metals can affect the density, strength, fracture, toughness, plastic deformation, electrical conductivity, and environmental degradation. Unlike pure metals, many alloys do not have a single melting point. Instead, they have a melting range in which the material is a mixture of solid and liquid phases. Alloys can be designed with a single melting point, and these are called eutectic mixtures. Properties of metals and metal alloys. At least good but usually excellent thermal and electrical conductivities. Relatively high densities, especially compared to polymers. Materials with high densities often contain atoms with high atomic numbers, such as gold. However, some metals such as aluminum and magnesium have low densities and are used in applications that require other metallic properties but low weight. Fracture toughness. Ability to avoid fracture, especially when a flaw is introduced. Plastic deformation. Lead poisoning. Satanism, plumbism or painter's colic. Neurological problems. Reduced IQ, nausea, abdominal pain, irritability, insomnia, excess lethargy or hyperactivity, headache, and in extreme cases, seizure and coma. Gastrointestinal problems, constipation, diarrhea, abdominal pain, vomiting, poor appetite, and weight loss. Other associated effects are anemia, kidney problems, and reproductive problems. Lead toxicity often causes the formation of bluish line along the gums, which is known as Burton's line. Restriction of hazardous substances directives. Directive on the restriction of the use of certain hazardous substances in electrical and electronic equipment. This took effect on July 1, 2006. Forbidden substances. Lead, mercury, cadmium, hexavalent chromium, polybrominated biphenyls, polybrominated diphenyl ether. The maximum permitted concentrations are 0.1% or 1000 ppm, except for cadmium, which is limited to 0.01% or 100 ppm by weight of homogeneous material. Limits do not apply to the weight of the finished product, but to any single substance that could be separated mechanically. Ceramics and glasses. Ceramics, often broadly defined as any inorganic non-metallic material. Examples of such materials can be anything from sodium chloride, table salt, to clay, a complex silicate. Metallic plus non-metallic elements joined together by ionic and or covalent bonds. Crystalline, polycrystalline or amorphous. The last one is sometimes treated as a different category, glasses. Glasses, an inorganic non-metallic amorphous material, does not have a crystalline structure. Examples of glasses range from bottles to the extremely high purity silica glass in optical fibers. Properties of ceramics and glasses. High melting temperature, low density, high strength and hardness, water resistance, corrosion resistance. Many ceramics are good electrical and thermal insulators. Graphite, electrical and thermal conductor. Low to null ductility. Low fracture toughness. Some ceramics have special properties. Magnetic materials, piezoelectric materials, superconductors at very low temperatures. Plastics, polymers. Polymer is equal to several parts, typically organic materials, but could be inorganic like silicons. Offer poor protection levels, but they are cost-effective. Electrical characteristics: high resistivity, insulator, low dielectric constant, less than 4. Thermal characteristics: bad thermal conductivity, low coefficient of thermal expansion. CTE for T lesser than Tg. Thermal stability up to 300 degrees Celsius for some compounds. Good mechanical properties: high water and solvent absorption, good adhesion. Glass transition and melting point. Glass transition temperature, melting point, temperature of fusion. Glass and melting points of polymer will determine which applications it will be suitable for. Many industrially important polymers have glass transition temperatures near the boiling point of water, and they are most useful for room temperature applications. Some specially engineered polymers can withstand temperatures as high as 300 degrees Celsius. Characteristics of a package: thermal performance, ability to dissipate the heat generated by the IC. Signal integrity, to ensure that the package parasitic inductance and the capacitances do not distort the input-output signals. Power distribution. The package must be able to supply enough current for the IC to work, and it must also be capable of handling the highest current peaks. Manufacturability. The best package is useless if it cannot be soldered. It should not require excessive handling precautions. Testability. To check if all pins have been correctly soldered. It is also about its prototyping capabilities. Reliability. The package must provide a good long-term reliability even in the harshest environments. Thermal behavior of a package. For modeling the thermal behavior of a package, a comparison to this circuit is used, where the intensity is the power dissipated. The thermal resistance means the ability of the package to remove the heat, and the voltage relates to the temperatures. This model just says that the increase in the junction temperature respect to the ambient one is proportional to the power dissipated and the thermal characteristics of the package. Thermal resistance. The thermal model of a package can be very complex. Moreover, it may have a heat sink over it, or a forced flux of air, etc. So, the thermal resistance is often splitted into resistance from junction to case and resistance from case to ambient. Some thermal aspects in package design. Cavity up or cavity down packages. Thermally enhanced packages. TI. Electrical model of the package. Spice simulation strong driver. Spice simulation weak driver. 10 MHz square signal with 5 ends fall and rise times. Pin inductance 50 Nh. Parasitic capacitance 50 pF. Parasitic capacitance as function of the interconnection level. Crosstalk. Crosstalk occurs when a line or a pin, aggressor, induces some voltage changes in other line or pin, victim, via their mutual capacitance or inductance. These two parameters depend on the geometry of the package, and the mutual inductance also on the proximity of a ground pin or plane, length of ground loops. Power integrity and distribution. The power and ground pins are no longer despicable in comparison to the input and outputs. Ground bounce. When many input-output simultaneously switch from 1 to 0, a sudden current surge goes through the GND leads parasitic inductance, causing the chip ground to bounce. A similar phenomenon happens to VCC sag, but historically has been less worrying because the increased voltage margin for once. In 5V TTL, 0 goes from 0 to 0.8 volts, but a 1 is anything between 2.0 and 5.0 volts. Power or ground count. There are many reasons for the recent increase in the number of power and ground pins. To reduce the parasitic resistance so that the power consumption requirements of the integrated circuit are fulfilled. Several amps. To reduce the parasitic inductance in order to eliminate the ground bounce and VCC sag problems. To ensure that there is a ground pin close to each input-output pins so that the ground loops are minimized and the crosstalk is eliminated. High-end devices at the package level currently have 8-1-1 input-output power-ground relationship. Using flip chip, the number of power and ground pairs at chip levels is much higher because there are many bumps connected to the power and ground planes created in package substrate. Evolution in power and ground layout. Manufacturability. PCB requirements. Minimum size of the tracks and paths. Pin pitch. The higher, the easiest. For the same number of input outputs, BGAs have much higher pitches. Solderability. BGA's self-alignment versus conventional SMD self-misalignment. Handling precautions. Plastic packages tend to absorb moisture that may cause the package to crack during soldering. Bottom line, always keep in contact to your PCB manufacturing and mounting partner. Testability. While BGAs are good in almost every field, electrical and thermal performance, solderability. Their verification capabilities are very poor. No access to input-output signals. No way to view the paths to assess the quality of the soldering. Automated verification approaches are needed. X-ray inspection may also be needed to ensure the quality of the soldering process. Or special optical fiber cameras. Fine pitch plus BGAs is equal to prototyping over. Fortunately, there are companies who build sockets for almost everything. Example, emulation technology. Knob lock for multiple insertions and extractions of chips. For example, in test and burn-in. Screw lock for prototypes and pre-production. ZIF, lever lock for pre-production and volume productions. Quick lock for test purposes, socket up to 80 pins. Quick lock for test purposes, socket as of 81 pins. Grip lock for test purposes. Reliability. Plastic packages are best suited for controlled environments. For example, low moisture and applications not requiring long-term storage or extreme temperature cycling. Ceramic packages offer the best performance in terms of thermal characteristics, moisture absorption and endurance in harsh environments. Moisture permeability in orders of magnitude better than in plastics. Moisture is the most important cause of corrosion. Qualification tests impart varying extent of stresses on the packages. The purpose is to accelerate any potential failure mechanism, which may occur during actual operation, temperature cycling, high pressure and high moisture, etc. The manufacturer provides reliability data based on these tests. Fabrication process certification, QML, MIL, PRF 38535. Package types. The basic types are shared among manufacturers, but each manufacturer has its own nomenclature for the variants, acronym salad. Fundamental types of integrated circuits: DIP, PGA, CLCC, SOP, PLCC, QFP, BGA. Specific types of discrete and passive components. Example of integrated packages. Dual inline package. Pin grid array. Ceramic leadless chip carrier. Small outline package. Plastic leadless chip carrier. Quad flat pack. Ball grid array, reduced pin count devices, TO92, TO220, TO3, SOT23, TO236, SOT223, TO261, TO263. Passive components, through-hole, surface mounts, SMD. Advanced packaging multi-chip modules, MCMs. Increase integration level of system, smaller size. Decrease loading of external signals, higher performance. No packaging of individual chips. Problems with known good die. Single chip fault coverage up to 95%. MCM yield with 10 chips. 0.95 into 10 equal to 60%. Problems with cooling. Expensive. Yield. Die cost is F. Die area 4. Pentium Pro. Example of commercial MCM. CPU plus separated on package level 2 caches. Chip stacked packages. Currently based on wire bonding, but there is research on flip chip. Used for example in memory devices for mobile applications. Flash plus SRAM. Examples of chip stack packages, Intel. Chip-on board mounting, COB. Chips are directly mounted over the PCB using a wire bonding technique very similar to the one used in packaging. Drawbacks. Obtaining known good dies. Component storage. Conclusion. Thus, we have learnt about quality assurance and standards and the following in detail. Electronic packaging.